As today we'll be doing a great circle sailing problem. This is a really long question, so you need to be a bit patient and go through this slowly. If you don't understand any part of this video, just pause it and watch it again. Alright, so let me start off by highlighting the two positions which are given to us, position A and B. And what we have to do is basically find the initial course, the distance between the two positions, and the position of the vertex along the great circle. Additionally, we'll also be finding out where the track cuts the longitude of 37 degrees west and 50 degrees north, situated on the track between A and B. Right, so let's start by drawing a diagram. Now both the latitudes are in the northern hemisphere, so we draw the pole towards the northern hemisphere. If they were in the southern hemisphere, we draw the pole towards the southern hemisphere. And if one of the positions was in the north and the other in the south, we normally draw the pole of the high latitude, latitude which has a higher value. We draw the pole towards that latitude. All right, so if this is the pole, P is the pole or the north pole in this case here. If latitude A is located from the equator at 51 degrees and 23 minutes, then PA, or the distance from the pole to the latitude, will be 90 minus 51 23, which will be 38 degrees 37 minutes. All right, I know the approximation is not very accurate here, but just bear with the diagram. All right, the second one is again B. B is about 46 degrees located from the equator, so PB would be 90 degrees minus 46. The distance between the pole and the latitude would be 90 minus 46, which is 44 degrees here. Angle P is the D long between longitudes A and B. Now in this case, both the longitudes are in the western longitude, so all we do is subtract one from the other. So if one longitude is 049, the other one is 009 degrees. If you've seen my other videos, you know how to calculate a D long. If they are both in the same side, such as west, and you just subtract it, and the answer that you should be getting is 03924 minutes. And the vessel is proceeding on a westerly route from A to B. All right, something like this is how the vessel is going. So this is the first part where we draw the diagram correctly and label it correctly, because you need to use these values to find out the rest of the values. So we'll start with finding out the great circle distance AB first. To do that, we go back to the spherical trigonometry principles, where if you have the included angle, which is angle P in this case, and you have the sides next to it, such as PA and PB, if you know those three values, you can find out the values of the rest of the triangle as well. So that's how you write down the formula. You write down cos P, which is the included angle, in the side opposite to it, which is cos AB, minus cos of the remaining two sides, which in this case is PB and PA. These are also the sides which include the included angle P. And then in the denominator, we write sine PB and sine PA, which are the same sides, such as cos PB and cos PA. It's just that we change the sine to sine and sine. All right, but what we need to find out is AB here. So we need to do a bit of an adjustment with the equation here. So take the denominator here, division becomes multiplication, and we also take this part on the other side, so which is a negative sign becomes positive, right, which will give us this equation here. Cos AB equals cos P multiplied by sine PB multiplied by sine PA, in addition to cos PB times cos PA. Now we know the values of P, PB and PA from the diagram above. Just put in those values in your calculator and track the values with those given by me in this calculation here, and make sure your values match mine. In case they don't, check again. So as a result, you will get AB as 26.22 degrees, but AB is a distance, so we need the answer in distance. So all you have to do is just multiply the whole value by 60, and the distance, or the final answer that you get, is 1573.5 nautical miles. This is the great circle distance between A and B in this case here. For the remaining of the question, we will be using AB as 26.22 degrees as calculated above. To calculate the initial course from A, initial course is the angle A in the diagram here. You can see the internal angle A here. This is the initial course. The vessel is on an initial course A. This can be, in this case, it looks like a southwesterly course if it was straight lines. But these are curved lines. These are great circle courses. They are drawn as curves on the mnemonic charts. So it could be a northwest component as well. So it can either be in the northwest or it could be in the southwest. Now how do we decide that? If it is less than 90, that means it's still in the northwest quadrant. If it is more than 90, that means the vessel is on a southwest quadrant. Alright, so let's start here. So your initial course is cos PB, which is cos A is the initial course, is the included angle. Then you write the side opposite to it, which is PB, and then the remaining two sides and the cos of the remaining two sides and the sine of the remaining two sides in the denominator. That's how you get your initial course. Simply put in the values this time and match the values given by me in the calculation here. They should match. In case they don't, check your values again. I have stuck to 5 decimal places because that's what popularly it is done. You can go up to more, it will give you more accuracy, but 5 decimal places is good enough. 2 would be too less, but 4 to 5 decimal places gives you good accuracy, which gives you the initial course as 86.2 degrees. But courses cannot be in decimals because you cannot steer decimal courses. Courses have to be in round figures. That's why I have rounded it off to 86 degrees. Because it is less than 90, that means if the vessel, if this is north, west and south, the vessel, although it seems like it was going on a southwesterly component, because it's less than 90, it's still here in the northwest quadrant. It's like a curve. So initially the course will be south northwesterly because the value is less than 90. That's why I have written A as north 86 degrees west, which is equals to 274 degrees true, right? So north 86 degrees west will be measured here. Somewhere here is your 86 degrees, and if this is 270 and 360, this is about 274 degrees true. That's your initial course. But you got the quadrant right. Northwest is the quadrant. That's what you need to predict the position of the vertex. What you also need is how to find out the final course. To find out the final course, we first need to find out internal angle B in the diagram, cos B. So we use cos B and we use a similar formula as we have done previously. Put in the included angle, the side opposite to it, and then the sides next to it, and as explained above. Simply put in the values here as I have. Once you put in the values in the calculator, you should ideally be getting B as 63.7 degrees initially, but you round it out to 64 degrees because the decimal place is more than 0.5. Your B is 64 degrees. Now if I go back to the diagram here, your B is 64, that means your internal angle B is 64 degrees. Just your internal angle was 86 degrees. But what I need is the final course here, and the final course will be something like this here. The vessel will be on a course here, right? So you need to find out the external angle B. Now if I draw another diagram here, it might make your understanding easier. Alright, so if the vessel is transiting like this here, this is B here, you need to find out the outer angle to find the course as measured from the pole. So what you do is subtract it from 180, because each quadrant is 180 degrees, right? Each quadrant is 180. This is not each quadrant, but the sum of two quadrants is 180. Alright, so this is a northwest quadrant, so subtract it from 180. What you find here is 64. Subtract it from 180 to get the outer angle here, and what you get is 116 degrees. When you get 116 degrees, this basically means that your vessel is now on a course of more than 90, which means it has moved out of the northwest quadrant now and gone into southwesterly quadrant. Alright, so 90 degrees, each quadrant is 90 degrees, but you are on a course of 116, which means you have overshot the northwest quadrant by 26 degrees. but if measured from southerly component, your course is south 64 degrees west. And that's what I put here, south 64 degrees west. If you need the true course, then this would mean 180 plus 64, that is 244 degrees, right? But all I need is the quadrants of the final course to predict the position of the vortex. All right, so sorry about that. So your initial and final course, when in different quadrants, your vortex will lie between position A and B. So in this case, your initial course was in the northwest quadrant, as understood above, and your final course is in the southwest quadrant, as we found out before. So because they're in different quadrants, the rule of thumb is then the vortex lies between A and B and always lies towards the higher latitude. If both the courses were in the same quadrant, vortex would lie outside A and B towards the higher latitude. All right, something like this probably. But I'm going to delete that now because you don't want that right now, otherwise it will cause you confusion, right? So vortex lies somewhere between A and B, and to find out the vortex we use the principles of Napier's rules because it is a right angle spherical triangle where angle V is 90 degrees. Now to use Napier's rules, we just take any one triangle. I am taking triangle APV. You can take triangle PBV if you want, but I am taking triangle APV, right, which is this triangle here. Here vortex is 90 degrees. You write down AV, which is the side next to the vertex angle, and PV, it can go in any order. Then the angles opposite to it with the 90 degrees minus from 90 degrees, and then the remaining side, which is 90 minus PA. Alright, so I repeat myself. You write the right angle triangle V 90 degrees outside the circle. Write the sides next to it. AV and PV are the sides next to the 90 degree angle. Then the angle opposite PV is A, so you write 90 minus A. The angle opposite AV is P, you write 90 minus P. And then the remaining side is PA, you write 90 minus PA. Alright, then you need to have two things in this circle to find out the rest of the two. So what I know in this circle is PA because I have found it out before, and I know P angle A, this is the initial course angle. I need to find out PV because that will give me the distance from the pole to the vertex, and then I can find out the latitude of the vertex. So I will use the rule cos of the middle equals, sine of the middle equals cos of the opposites here. Put sine of the middle as PV and cos of the opposites as cos 90 minus A and cos 90 minus PA. Cos 90 minus A is also equal to sine A, or cos 90 minus PA is also equal to sine PA. Alright, since we need to find out PV, just follow my prompts here as I have shown you in the calculation. Put in the values. What you should be getting is PV equals to 38 degrees 30.9 minutes. Now remember, PV is the distance from the pole to the vertex. That's not the latitude. To get the latitude, which would be from the equator here as a reference point, to get this distance here, all you need to do is subtract the value from 90 degrees. So PV will be 38 degrees 30.9, but to find out the latitude of the vertex, subtract it from 90 degrees and you get the value. You know you are still in the northern hemisphere, so of course it will be north. So that's how you get the latitude of the vertex. To find out the longitude of the vertex, you need to find out angle P here, because that would give you the D long between A and V. Now if you know A and PA, use the ones that you knew before, and don't try to use PV in your calculation, because if you have made any error, then you will continue with that error. Alright, so what we then use is these three values. So we put PA in the middle and then tan of adjacents as per the Napier's rules, right? So sine 90 minus PA then becomes tan 90 minus A multiplied by tan 90 minus P. You need to find angle P, so you need to do a bit of adjustments with the equation. Your known stays on the one side, the unknown goes on to the other. Put in the values here as I have. Follow my prompts given here. What you should find out is P will be equal to 4 degrees and 51.5 minutes. Now why I have named it west is, if I go back to the diagram here, you can see that A is in the west longitude. Let's go back to the first diagram, then it will be clearer because I have written down the values of the longitude there. So A is in 009 36 minutes, B is 049 degrees. The vessel is going further west, so the vertex is located further west of A, right? So if I go back here, you can see the vertex is located further west from A, so the west longitude has to be increasing, and that's why the D long will be west here, angle P. So you have longitude of A as a reference, then you have D long or angle P that you've just calculated. To find out the longitude of the vertex, you will add to the west longitude because you are going further west, and the answer you should be getting is 014 degrees 27.5 minutes west longitude. Continuing on this longer question, if on the same question I ask you where does the track cut the longitude of 037 degrees west, you know that 037 degrees west would be somewhere west of the vertex. So if the vertex was 014 degrees 27.5, you know that, let's call it the point M, you will be cutting somewhere here is 37 degrees west would be west of the vertex. Now what we do is, then we need to find out the latitude of M. To find out the latitude of M, we need to find out PM in triangle PVM using spherical trigonometry as before. In PVM, we know PV as we have found it out before when we were calculating the latitude of the vertex, and we also know angle P. Why is that? Because P becomes the D long between V and M, because we know the longitudes of both these places. So because we know the longitudes of both these places, P becomes D long between V and M. They are both longitudes are west longitude, so you just subtract it. You can take the smaller number and subtract it from the bigger number, and angle P you will get as 022 degrees 32.5 minutes. So that gives you angle P as well. All you need to do is find out PM. If you need to use these three in one equation, then P becomes the midpoint, and tan of adjacence is the rule that you will use for Napier's rules. So that's what I've done here. Sine 90 minus P will be tan PV multiplied by tan 90 minus PM. Alright, then just use the prompts that I have given here. You need to find PM, so that's why I've transposed the equation, keeping my known to the one side and taking the unknown to the other side. Put in the values here, keep going, see the prompts that I've given in the question here, the answers that I've given, match these answers, recheck them. So what you should be getting as PM is 40 degrees and 45.1 minute, but this is PM. This is the distance from the pole to the point M where the 37 degrees longitude is cutting the track. To find the latitude of M, as I have explained before, you will need to subtract it from 90 degrees to find out the latitude of M. This is what I've done here. The answer that you should be getting is 49 degrees 14.9 minutes north, still in the north hemisphere. Finally, if I need to find out where does the track cut the latitude of 50 degrees north, I go back to the same diagram. Let's call this point N, and if this is the latitude 50 degrees north, I need to find out the longitude. Then now if I know the latitude N, I will know Pn will equal to 90 minus latitude of N, which is 50 degrees. So I know Pn is 40 degrees, right? I will take this triangle here, PVN, because it's a spherical triangle. I can use Napier's rules to solve it. And what I need to do is just find angle P in this triangle, because this P would give me the D long between N and V, which I can then apply to the longitude of the vertex, which is known to me, and get the longitude of N. So in this case, PV is 38 degrees 30.9 as I've calculated it before. PN is 40 degrees as I've explained before. All I need to do is find out P, include these three in the same equation, two knowns and one unknown. Transpose it here, we use tan of adjacents. Sin 90 minus P is also equal to cos P. Put in the values here. What you should be getting P is as 18 degrees 28.4 minutes. Now this P, like I've explained before, gives you the D long between vertex and the point N. As you see in the diagram, N is also west of the vertex, and as we are going on a westerly route, the vertex longitude, from the vertex longitude westerly, the west longitude should be increasing, right? So we have longitude of the vertex as 01427.5. Point N is west of the vertex, so we'll add to this to find out the longitude of N, which is 32 degrees 55.9 minutes, right? So remember, if we have to find out latitude of any intermediate point, we find out P to the point latitude, which is in this case could be PM, which was in the previous case was PM. If I need to find out the longitude of an intermediate point, I need to find out angle P between the two positions. Familiarize yourselves with the Napier's rules to make sure that you can apply them in cases of right angle spherical trigonometry. This is a very long question, so you need to be patient. You need to watch these videos multiple times to get an idea of how to do it. Otherwise, it's pretty simple, pretty straightforward. You just need to be patient. You need to recheck your calculations every now and then to make sure that you're not committing an error, because once you commit an error at the very first step, you pretty much carry this error throughout the question. All right, watch this video multiple times, pause it where you can't understand it, rewatch it, and get a good idea of how to solve a great circle sailing question where you have to calculate the initial course, distance, the final course as well, to calculate the position of the vertex, and also to find out the position of the intermediate points.